Hello, it's Mr. Shrum, and I am back to finish up the Introduction to Waves tutorial. And we left off at the electromagnetic and mechanical waves. So let's get into that. Electromagnetic and mechanical waves. If you go back to that wave simulation before, you saw a transverse wave move up and down on a string. You saw the way in which energy moved through a medium, one particle at a time. So can you imagine the movement of wave energy from one point to another without a material medium? That brings us to the sun. The sun is very active and its surface experiences changes, shock waves, and vibrations. However, none of these mechanical vibrations ever reach Earth because there is no continuous medium of gas, liquid, or solid in space to transmit them. An observer on Earth cannot feel, hear, or detect mechanical waves from the sun. And yet the sun also emits light waves. Light and other electromagnetic waves can travel through empty space. So we are able to see the sun's light on Earth. Let's investigate mechanical and electromagnetic waves in more depth. Mechanical waves. In the lesson activity, the energy that traveled through the string came from the original disturbance. And that disturbance displaced the first particle of the medium above its position of equilibrium. And equilibrium is where it sits at rest when nothing's happening. Because the particles of a material medium, such as air, water, or solid earth, are in contact with one another, energy in one particle can transfer to an adjacent particle. Imagine that each particle of the medium is connected to a successive particle by a tiny little string. So imagine this is a particle, and there's a tiny little string attached to another particle. In this way, energy moves from one particle of the medium to the next, and a mechanical wave is created. Waves that can't travel through a vacuum and always require a medium are called mechanical waves. These are sound waves, ocean waves, earthquakes, and the vibrations on a string are all mechanical waves. Mechanical waves can sometimes be changed to different types of waves when the vibrational energy is transmitted from medium to medium. An earthquake near the coast or under the ocean can transmit energy to water, creating a destructive high-energy ocean wave called a tsunami. If you remember learning about tsunamis in other classes. Just giant ocean waves created by disturbances. And a tin can telephone, like the one over here in this photo, can begin with a longitudinal sound vibration inside one can, create transverse vibrations along a stretched string, and then finally emerge from the other can as longitudinal sound waves. So they can morph. Mechanical waves can morph. On the other hand, we have electromagnetic waves. The sun's light travels to us from millions of miles away. Since the time of Isaac Newton, the scientific community explained light's journey from the sun to the earth through the concept of ether. Ether was this supposedly invisible, undetectable medium called ether. And it was said to be present in space that allowed for the movement of light. Although any experiment to verify the existence of this mysterious medium proved fruitless. They couldn't prove it. It was accepted explanation for light travel for centuries. So hundreds of years, people thought this way, and it's just not true, as we have come to find out. Near the end of the 19th century, so think late 1800s, two physicists in Ohio used the speed of light to devise an experiment named the Mickelson-Morley experiment. And that made it virtually impossible to support the idea of an ether. Eventually, their surprising discovery helped lead to Einstein's theory of special relativity. Also in the 19th century, so still 1800s, Scottish scientist James Clerk Maxwell developed a theory to explain a new type of wave that was largely invisible and could travel without a medium. He found that electric and magnetic waves existed together. He called these waves electromagnetic waves, so electric plus magnetic. Understanding that visible light is a form of electromagnetic radiation helps explain how light can travel through empty space from the sun to the earth. Here we have a video talking about radio waves, gamma waves, and ultraviolet waves, or UV rays. And these are all electromagnetic waves. Electromagnetic waves travel at the speed of light until they interact with matter. In this video, it talks about how frequencies and wavelengths of various types of electromagnetic radiation compare. And the key difference between mechanical and electromagnetic waves is that electromagnetic waves can travel in a vacuum. So light can travel in a vacuum. Radio waves can all travel in a vacuum. On the other hand, mechanical waves, it needs a medium to travel through. So it needs some type of air, some type of water, some substance to move. In a vacuum, mechanical waves cannot move. Another key point to remember is that all electromagnetic waves are transverse. Electromagnetic waves are transverse. Mechanical waves can be either transverse or longitudinal. And you can go through that video. I can't show it all here because my video will get taken down, unfortunately. What is the key difference between mechanical and electromagnetic waves? We just discussed this, so testing your understanding. Electromagnetic waves can travel in a vacuum. It does not need a substance or medium, but mechanical waves do need a medium. So think of mechanical, medium. Mechanical waves need a medium. And that brings us to the summary. So let's return to the example of a crowd doing the wave at a football game. The particles of that wave's medium, which are the spectators, the fans, they don't move from their position, but the wave itself moves all around the stadium. Although not a wave in the scientific sense, this wave demonstrates the way particles in a medium move to transfer the energy of a wave. Waves are essentially disturbances that transport energy through matter or space. Waves that need a medium to move are called mechanical. The medium a wave travels on is made up of interacting particles that vibrate to pass on the wave's energy. When the particles of the medium vibrate in a direction that is perpendicular to the motion of the wave, that is called a transverse wave. When particles of the medium vibrates in a direction that is parallel to the motion of a wave, that is longitudinal. That's a longitudinal wave. Electromagnetic waves don't require a medium for transmission. They are transverse waves formed by intersecting electric and magnetic fields. And these fields, composed of electric and magnetic waves, are vibrating perpendicular to each other and are also perpendicular to the direction of the magnetic wave. And we'll learn more about that later. But remember, all electromagnetic waves, including light, are part of the electromagnetic spectrum. And that's it. So thank you for sticking through the introduction to waves. And next time, we'll talk more about waves and use some mathematical equations too. So until then, have a great day, and I will see you all later. Bye.